All right, here we go. Tuesday morning, e-learning day for you. Let's talk some parallel circuits here. Okay. I am currently on slide 65 of the slide deck. So I would encourage you, or sorry, 66. I would encourage you to follow on with what's going on here. Okay. When we talk about resistors in parallel, now this is a little bit different circuit than what we've seen before. Okay. So when we look at these now, what we're going to see is that we go from just one resistor over here, right? And even, you know, early or late last week, we put a resistor there, which now for us is going to be on its own circuit. Okay. So what we've done here is that we've added an entire new branch for our current to run through. So previously, our current would have ran through there, and then ran back through there. Okay, meaning that it would have had that one direction, it would have had that one path. Here now, we get multiple options. So now it can either take a right there or it can go straight there, right? It's kind of like how if you were to pull up on 185th right across from Century Middle School, and all of a sudden you saw, a dump truck here and a regular car here, right? Well, you like current are going to take the fastest route. So you're going to take that route until it becomes so that it's not faster anymore. Okay? So what we see is that we see this split current here, and that's what starts to happen for us. So we start to see that our I total becomes this I1 and I2. Now, as this thing starts to run through here, what you're going to notice is that, let's say that this is a 12 volt DC source, right? As it gets to this point here, it's still 12 volts. Still 12 volts, because the only way that this is going to lose voltage is by going through a resistor. Going through wires should have a minimal effect on it, like we saw in lab the other day. So if it decides to go that way, well, it's still 12 volts right to there. Also, if it chooses to go that way, it's still going to be 12 volts there. So once it hits either of these two, they get all 12 of the volts. All right. Now, again, the odd part of this is that once they do go through there, then they're down to 0 volts. Then it's going to take all of them, right? So in this case, those resistors get all of that voltage. And then as they run out of it, they run out of that pressure, they run out of that energy. Okay. So what we start to see is that as we look at this, we're going to notice that this 12 volts now starts to stay the same. Our current, though, what we're going to see here is our current can be split between those two. Now, obviously, if these are two equal resistors, if they're both, let's say, hey, knock it off, Snoop. If they're both 6 ohms, sorry about that. Snoop's being overprotective of absolutely nothing. What a shock. All right, if both of these are 6 ohm resistors, and we know we've got 2 amps of current running through there, well, of course, this is going to split nice and evenly. So that would be 1.0 amps. That would be 1.0 amps, right? Now, if they aren't the same, well, that becomes a little bit more of a different issue for us, but we'll deal with that once we get there. Okay, so the formula that you need to write down is right up here. 1 over R parallel equals 1 over R1 plus 1 over R2. And this becomes a big deal for us because this is a little bit more of a challenging equation than what we've had before. Meaning that once we actually put in our values for R1 and R2, we still have 1 over R parallel to contend with. So likely what you're going to see is that when these two R1 and R2s are added, this number is going to be below 1 basically. So it's going to be 0 point something, right? Don't write that as an answer because what we need to be able to do there is we need to be able to take 1 divided by whatever this answer is here. Okay, so just make sure that you're aware of that. Make sure you make that subtle change there once we get to that point. Okay, series versus parallel electric lines. For us here, resistances are going to add up, meaning that we're going to take that R1 plus the R2 plus as many as we have, and that's going to equal our total. Current stays the same. Remember, this thing just has one path through it. And so because of that, what we're going to see is that the I is the I throughout the whole entire thing. And then with each resistor, right? So in that circuit, if we have two resistors like this will take some of the voltage. This will take the rest of the voltage. So those two together are going to equal RV total. All right. So that's series. That's something that we've seen. When we talk parallel now, what you're going to notice is this has multiple branches. So because of that, our resistances are going to be the total, which is on the bottom, are going to equal R1 and 1 over R2. All right. Current here has options. It can go to the right here. It can go down and around there. Again, our current is going to change based on the resistance. If we have an R2 here that has a high resistance, right, then it's going to slow that current down a lot, whereas the other current will be faster. Voltage now, this is again a little different than what we saw before because that voltage as it goes here, there's nothing to steal that voltage. So again, if we've got an 8-volt DC source here, right, as soon as it gets to this point, it's still 8 volts because there's nothing to absorb that or take away that voltage. As soon as it makes that right turn and goes down the top circuit, or top portion of this, it's still just 8 volts. If it decides to go straight, that's still just 8 volts. Makes a right turn there, it's 8 volts. All right, meaning that until it hits an actual resistor, that's going to be the only point in time where we start to see that being lost. Okay, hopefully that makes sense for you. Tomorrow when we get back together, again, we'll talk it through and make sure it does. All right, let's try one. Okay, so for us here now, what we see is we've got a R1 with 10,000 ohms. Sorry, numbers are kind of crazy. R2 is 2,000 ohms, and R3 is 1,000 ohms. We can see we got a 9-volt DC source. You can see the positives up this way. So if we were talking conventional current, it would be going that way. If we we're talking electron current, it'd be going that way. All right, all that stuff is all good. We want to find the total resistance for this one. So to do that, 1 over RT, because this is a parallel circuit, because we've got one branch, two branch, and three branch, and all of them look like a picket fence or look like they're kind of parallel to each other. So we're going to go 1 over R1 plus 1 over R2 plus 1 over R3. All right. So then once we do that, let me get my calculator set up. Sorry about that. 1 over R total equals 1 over 10,000 ohms plus 1 over 2,000 ohms plus 1 over 1,000 ohms. Now, a couple different ways you can do this. I know you have the fraction button or that option on your calculator. You can also just go like this, RT to the negative 1, inverse basically, right, equals 10,000 to the negative 1 plus 2,000 to the negative 1 plus 1,000 to the negative 1. Again, your choice as to whatever you want to do here. All right, so if I take 10,000 in here, and then I do my 2,000 as an inverse and my 1,000, what I end up with is 1 over R total equals 0.0016. Now, at this point, people want to select this as our answer, but it's not because notice I still have RT down in the bottom of that. So I have to take 1 divided by that, take 1 divided by that. So if I do 1 divided by my second answer, my R total should be 625 ohms. Anytime we get our circuits here, and what we start to see is that we start to see that the total resistance in a parallel is going to be less than that of the smallest resistor. Whereas in series, we're going to see that this total resistance is going to be larger than the biggest one. Okay, to find total current, again, this is just V equals IR. We're just using Ohm's law. So if we've got 9 volts, right, that's our current, which we don't know. We got our 625 here, divided by 625, 9 divided by 625. My I equals 0.016. 0.0144 amps. All right. So basically what that means is that it gets to here, the I equals 0.0144 amps. Now, my voltage is still going to be 9 volts through there. Okay. If we want to find the resistance, or sorry, the current through R3 out here, sorry, through R3 out here, what we have to remember is that this current is going to get split, split, split. So it's going to get split 3 different ways, depending on which one is the biggest and which one's the smallest. This one being the smallest, it'll probably be the fastest. The one thing that stays the same is that that's going to have 9 volts going through it there. That's going to have 9 volts going through there. That's going to have 9 volts going through there. So what we're able to see is if we want to solve for the current through R3, once again, we don't know what that is. So we're going to use Ohm's law here. V equals IR. At this case, again, we've got 9 volts running through there because there isn't anything at this point to change that voltage. We don't know the current through R3, but once we look at the at the resistance of it, that's 1,000 ohms. All right, divide by 1,000. I equals 9 divided by 1,000. So this is going to be 0.009 amps. All right. Now, one thing we notice, and again, this is the teacher in me, we can see that that is still less than what we had up above. So that's a good thing. If all of a sudden we got amperage higher than that, then we're going to have a few little issues there. Okay. Here's what I'm going to encourage you to do. All right. On slide 73 on the slide deck, go through and try to take care of this problem here. All right. I've got answer keys on the actual slide deck. I'll put up a quick set of homework as well after this video gets posted. Take a look at a couple of them, see if you can feel comfortable doing them. And then tomorrow when we get back into school, we'll talk and make sure that we're feeling comfortable about parallel circuits. We'll also run lab on this stuff. And then on Friday, we'll put everything together. Okay. Hey, stay warm. Take care of yourselves. All right. And we'll hope to see you tomorrow in school. All right.